For the next 30 minutes, we're going to have a presentation from a vendor named Edgewise from a gentleman named Peter Smith. Peter is the Edgewise founder and CEO, self-described serial entrepreneur who built and deployed Harvard University's very first NAC system before it even was a security category. I really love that we've got Peter on. I'll be honest with you. We actually talked to Peter on Security Weekly about a month ago or so, and I really enjoyed his presentation and his approach to some of the things that he's doing at Edgewise, which are fairly innovative and rather unique. And so I think this will be an enjoyable presentation. Pete comes from a lot of experience, 10 years of enterprise expertise as an infrastructure and security architect of data centers and customer hosting environments for Harvard University, Endeca Technologies, Oracle, American Express, Fidelity. And so Peter has had some interesting experiences in our industry, which should be no surprise to just about anybody in the industry who's presenting some unique solutions to today's challenges. So it's very interesting. Now, this is originally going to be our lunchtime talk. I imagine with the gap that we just had between the last presentation and now, a lot of folks probably did get out and get themselves some lunch anyway. So without further ado, I'm going to turn it over to Peter. We are just a little bit early, but I guess, Pete, you can just go ahead and kick it off.
Awesome. Thank you so much. I do apologize in advance to all of the viewers. I'm feeling a little under the weather and have a persistent cough, so I'm actually going to use a pre-recorded version of this talk that I've given many times. So apologies for that, but at the end I will take questions if there's time. So I hope you enjoy, and thanks for watching.
And so, Peter, just on that topic, we'll do a quick virtual elbow bump as per today's Corona protocol. I do hope that you don't have that particular virus, but we all should be aware and stay healthy for sure.
Welcome to today's webinar, Stopping Python-Based Backdoor Attacks. My name is Peter Smith. I'm the founder and CEO of Edgewise Networks. Today, we're going to talk about Python-based backdoors and how they're used in data breaches. Then we'll talk about the limitations of existing controls, and finally, how to prevent these attacks using a zero-trust approach. You likely heard about an Iran-linked threat actor that used a backdoor against the Turkish government. Now, Iran and cybersecurity aren't particularly interesting in today's news, but what was interesting is the technique that was used, specifically a Python-based backdoor that combined snippets found on the internet with some custom code. It turns out, if you go to GitHub right now and search for Python backdoor, what you're going to find is 230 results. The question is, why is it such a popular platform for building backdoors? And I think the answer lies in how pervasive Python is. It's installed by default on virtually every Unix operating system, and it's largely covert. If you look in a process table, you'll see a lot of Pythons that exist for legitimate administrative purposes. So it wouldn't be unrealistic to think that a covert Python script could be misinterpreted as an admin tool. And then third, it's incredibly easy to develop and to debug. We're going to actually build a custom command and control system written in Python in just a couple lines of code. I would go so far as to say Python is the PowerShell of the Linux and Unix world. Let's talk about the existing controls and the limitations they have. First, we've got stricter IAM to mitigate the threat of these Python-based backdoors. Unfortunately, IAM doesn't help you control what executes or communicates in your environment, so it's not going to be particularly effective. The next one is security groups, which are focused on communications, but they're not protocol aware. They're just a dumb firewall, and they lack default outbound controls. It's mostly about protecting inbound communication paths, and it's got a lot of limitations there as well. So firewalls, specifically NGFWs, they're very easy to defeat through obfuscation. Many of the techniques we're going to use today, like encoding, encryption, so on and so forth. And then the last would be microsegmentation, which in this case, we're talking about address-based microsegmentation, which gives you granular control, but has the limitations of security groups and firewalls. Namely, they aren't protocol aware, they're address, port, and protocol. They don't know what's really communicating. They can be defeated with encryption or basic encoding. So what we're going to do is go through a couple scenarios showing how it defeats these techniques or these protection strategies, and then show you the alternate protection strategy, which is an identity-based approach using a zero-trust model. First, let's talk about a couple scenarios. The first scenario is a basic listening socket that can receive commands from a remote attacker, but it has a number of limitations. The first limitation is that the attacker and the target have to both be on the internal network. So this is not a remote command invocation from outside your network. It is only remote command invocation from within your network. It's incredibly simple to accomplish, so let's take a closer look. What we're going to do is we're going to look at two systems. The first system over here is going to be the system that listens for remote commands. It uses a combination of Netcat and Python. You can see Netcat here is listening on port 8080, and it will keep open after a command is received. It'll then pipe it into Python with a -c, which means this is the actual Python script in plain text that it should execute. The script is incredibly simple. All it does is it says execute anything you receive via raw input, hence the receive via the pipe from Netcat. So execute the raw input after decoding it using base64. Everything that's transmitted is already encoded in base64, going in plain text across the network, will be executed locally via Python. Now the next system over here is going to send the command. All we do is we echo out a Python script. Echo out import OS, print OSP open with the ls-l command. We're going to do something very benign here just to prove the point, and then print it to the screen. Now, note, this is going to print to the system that executed the command. There is no ability to receive the response from this command executing with the Netcat-based approach. Then it encodes it into base64 and sends it to Netcat to be sent over to the remote command system. So let's fire this guy up, and then let's send the remote command, see what it does. What you can see here is that, sure enough, it did the ls-l and it printed it out to the screen. Now, again, this system has a number of limitations. Namely, it cannot be used by an attacker from the internet to control internal systems. So let's take a look at a more sophisticated system. Now, for this system, what we're going to do is, rather than demonstrate off-the-shelf backdoors with thousands of lines of code, I want to build a backdoor from scratch and walk through the anatomy of the system. It's my hope that by sharing the inner workings of these sorts of systems, that it's going to raise awareness about just how significant a threat they pose. But I should point out, this is absolutely unequivocally for educational purposes only. Please don't do anything nasty with this stuff. So we've got a couple goals in the creation of this system. First, we want to create a backdoor using the smallest possible footprint. Preferably fileless, and in fact, we are going to be fileless in this case. I want to make sure that we've got persistence so that if the administrator notices a rogue command and they kill it, that it doesn't remove our ability to do command and control. So to distill all of that down to 4 simple goals, number 1, I want it to always work. It can't use non-standard libraries. It's got to use what's on the operating system by default. Number 2, it's got to always be available. It needs to be resilient to faults as well as to attempts by the administrator to correct malicious behavior. Number 3, it has to be flexible. We need to be able to allow any code to execute. And number 4, it needs to allow remote invocation without listening sockets. I don't want listening sockets that require the user to be, or the attacker to be on the internal network. This thing needs to be able to allow remote invocation from the internet. So what we're going to do is write some code in a very procedural style. It's going to be functioning pseudocode, so to speak. Really, the point is, I want the intent of the code to be perfectly understandable to programmers and non-programmers alike. What we're going to do here is we're going to have a command and control system in the middle that is accessible from the attacker via a web browser. They can send commands and see responses over the internet through a web browser. And then we'll have software that lives on the target hosts that communicates with the command and control system to get the commands executed and send the responses back. All of this will be done via HTTPS and in just a couple lines of code. I think the entire system is 50 lines of code total. So what is the anatomy here? First, there's a preloader. The preloader is the thing that you are tricked into executing locally that gets this entire thing going. So it might be a watering hole attack where you copy and paste from a website and paste it into your command line, and now you are compromised. The next thing is the preloader loads the bootstrapper. The bootstrapper is the system that actually does the heavy lifting. It connects back into the control system and says, do you have any commands for me to execute, executes them, and then posts the results back so the attacker can see the output. The next is the persistence layer. It's not sufficient to just trick the administrator into running a command once. You need to have a foothold in the system so that if they try to remediate, it comes back again and again and again. And then the last system is the control system. This is the actual system the attacker interacts with to dispatch commands down to the targets. So with that, let's take a look at the preloader. The preloader is a very simple piece of code. What it does is a couple things. Number one, it checks to see if the bootstrapper is running. It checks to see if the cron tab has been updated for persistent. If we are not running the bootstrapper, it simply goes and gets it. So let's look at this. Python-C import requests so that we can do HTTP requests. The next section with URL lib3 you can ignore. It's just so that we don't post any sort of messages that might look incorrect to the administrator. The next is exec requests get. So all we're doing is getting a URL, which is update python.us/bootstrap, and executing that. Now, this is really important. We chose a URL of update python.us so it looks benign, and that is actually the command and control system. And all this is doing is it goes out to the update python.us, gets the bootstrapper, and executes it locally after it decodes it in base64. Again, everything is obfuscated with encoding. Now, the next thing it does is it goes and it tries to modify the cron tab, and it does something a little bit tricky on macOS. So if the cron tab has not already been manipulated, then if it's macOS, it sleeps for 15 seconds. Now, I think an attacker would typically do something that's much longer, like a minute or 5 minutes, because what this is doing is on macOS, if you modify cron tab, it prompts you to accept the changes, saying, do you want the terminal to be allowed to modify cron tab? The administrator has to click the OK button. What we want to do is disassociate the action of running the preloader with the request to approve cron tab manipulation. And we do that simply by delaying the action. Now, once that delay happens, then we simply append the current cron tab with this line, which executes our preloader every minute. And that is the entire bootstrapper. Now, the key is how do you get the administrator to actually execute it? So what we're going to do here is we're going to go and do a watering hole attack. So first, I'm going to start my controller, and we're going to go over to Google. Let's say I know that my target often uses a given service to look up IT information about how to remediate issues. Let's say it was Stack Overflow. The attacker is going to try to respond to the target with an answer that includes a malicious URL and trick the user into pasting it into one of their systems. So let's say me as an administrator, I go and I say install pip Python 3 Linux and Stack Overflow. And I've got a couple responses. How do I install pip with Python 3? Yeah, that looks good. I'm going to click on it. So as I look through this guy, oh, I've got an approved answer. I scroll down, I see a code block, which most of us would just look at that and copy and paste and move on with our day. You can see here, what I've got here is curl-ks HTTPS, update python.us preloader piped into the shell. So I mindlessly just select it and come over here and I say, okay, I'm going to paste it and background it and run it. Okay, did something, didn't look like it was bad, so I'm going to move on to my other system, do the exact same thing, and all right, it did something. So let's look at actually what it did. When I ran that command, which looked benign, I got it from a watering hole because the attacker targeted me, then what happens is it gets the bootstrapper. What we talked about before is the preloader modifies cron tab and then kicks off the bootloader. So let's look at cron tab. There it is, curl-ks update python preloader. Okay, so we're persistent. Now, what about, is it running? Yes, it is running. Python-C, there's my entire bootstrapper. So I'm going to kill this guy. I go kill-9, and okay, it's gone. Now, is it really gone, though? Because we modified that cron tab. And what we're going to see is within 60 seconds, I wish it could go faster, but unfortunately, that is the granularity I've got. Within the next few minutes, oh, there it is. It came back. So we've got our persistence. We've got our bootstrapper. Now, let's see what it's actually doing with the command and control system. For that, we're going to go over here, and we're going to look at the command and control system, which what you can see right now is a bunch of check-ins from linuser db01 and linapp-pay01. Those are the two systems that I've deployed this to. Now, it is interesting, taking a slight divergence. What about Windows? Well, guess what? The exact same script runs on Windows. That, yet again, is the power of Python. It's multi-platform. So we're going to go over to a Windows system and run the exact same thing and see if it starts checking it. All right, there's our Active Directory server, Windows box, AD02, right there at the top. So we've got 3 systems connected, 2 Linux boxes, 1 Windows box, going into this control server. Now, what is the control server doing, and what is the bootstrapper doing? So the control system is a very simple piece of code. We're going to do VI on control, and you can see there's a bunch of boilerplate here. It's a Flask app, which makes it even easier. And really the meat of this entire system can be wrapped up in these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 lines of code. And what this is doing is basically looking at a bunch of URL parameters, the arguments for the command and control system to parse out a target. What is the device we want to control? What is the command we want it to execute? And what is the response that we received after the execution was done? And this block of logic literally just says, if you've got a command, post it to the device. If you've got a response, post it to the device. If you post a device, show it what the actions are that have been happening. Very simple stuff here. Now, the question is, what does the bootstrapper do? So if we look at the bootstrap, again, some boilerplate up top, and then the bulk of the code is in this while statement. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 lines of code, including comments and white space, to accomplish an entire bootstrap. And all this does is it says, while true, meaning run this infinitely, I want to get the commands from the control system that are registered to my hostname. And all it's literally doing is saying, execute the process open, do a request to this URL, which is HTTPS, so it's all encrypted, to update Python, specify the target. The target in this case is the hostname, and then get the commands that should be executed. So this block of code, 1 line, this is what executes the remote commands. Now, once the command is executed, this is the 1 line. I've done some line breaks to help it with readability, but it's actually just 1 line of Python. This 1 line posts the response to the command invocation to the command and control system. That is it. The only other thing interesting here is that we randomized the interval for checking into the command and control system. I've done it with a very small interval, which is like between 1 and 3 seconds randomized. I think typically an attacker would try to randomize it with much broader periods of time because they don't want you to see this periodic spike of connections out to updatepython.us. You might do it once every hour, and that would randomize within that 60 minutes so that you don't see a very predictable pattern across all of your systems. So we've got our preloader, which is the thing that tricks you into copy and pasting. That then establishes persistence and runs the bootstrapper. The bootstrapper simply checks to see if commands are available, executes them, and posts the results back up to the command and control system. The command and control system is a simple set of logic to say, do I have a command? Do I have a response? Are you asking for information about a target? So let's see how all of this plays out. We're going to run our command and control system. And what we're going to do is see that we've got our 3 devices connecting in. Now, can I dispatch commands? And how do I do that? Again, I just go to an HTTPS URL. So I'm going to come up here and I'm going to say HTTPS update Python US. It's going to prompt me to approve. And now what I see is a listing of all of the devices that are registered. It gives me a status showing the last time they checked in. If I hit the refresh, you can see that it's changed the timestamps of the last refresh. So what can an attacker really do with these sorts of command and control systems? And the answer, unsurprisingly, is virtually anything. But even though you know it's anything, the results will sometimes surprise you. So for instance, what if I wanted to look at the users on a given machine, like one of these Windows machines? So I say target equals AD02, and I say command equals the net user command. Great. So you can see it registered the command net user. Now, if we get rid of the command, we can see the result. The result is it listed out all the user accounts. We've got administrator, default, desktop, edge admin, so on and so forth. Now, what if I wanted to actually change the password of one of these? All I do is net user. I'll use the test account just so I'm not messing with anything. And I say, I'll just create a password, AA55. I want to make sure I meet those complexity requirements that were set, you know? And I run it. So did it execute correctly? Let's see the results. There it is. The command completed successfully, meaning we just remotely changed the password on that Active Directory server for the test user account. Now, what about the Linux systems? If I come over here and I say lin user dvo1, and I say I want to do a command which is netstat to see what it's communicating with. Great, it registered netstat an, and I get rid of the command here, and now I can see the results. So I'm looking at this guy and I say, oh, this looks like an interesting address. I want to scan that. So use nmap. But do I know if nmap is actually installed? Well, we can very easily find out just by saying command and then saying yum list installed nmap. It registered the command. Now let's see what the results are. All right, so that truncated response means that it is not actually installed. So what we can do then is just say command, and again, what we're going to do is very simple. We say sudo yum -y install nmap. So it's registered. Now let's see what it does. Still thinking about it. There it is. So there we go. Verified nmap installed, nmap complete. So we've installed nmap on the system via the command and control system. Now let's actually use it for something. So what we're going to do is nmap scan the address that we found from netstat. We just registered it. Now let's see what the results are. We can see port 22 is open for SSH and port 8084, which is an unknown protocol. But what about looking at traffic and watching the administrator do what they're doing? I could actually perhaps do a TCP dump. So all I need to do is say sudo TCP dump, and we're just going to look for one packet, and we'll look on port 53 so that we can watch the DNS request that they're making. So again, we need to encode this. So we do 26 for the ampersand and run that. Now, we don't make a lot of DNS requests, so why don't I just make one myself? I'm going to go and look up google.com. Great. So a DNS request has been made. Let's see what it says. There it is. There's the TCP dump output for my DNS query for google.com. This is obviously a big problem. And we need to resolve this using techniques that are effective against low-level Python script-based backdoors. So what is the answer here? The answer, in my mind, is identity. Identity is the answer because it truly identifies what is communicating, not just how it's communicating. Firewalls look at addresses, ports, and protocols, which is the means by which two things communicate, but it doesn't really tell you what is communicating. Identity tells you the cryptographic identity. That would be the signing certificates, the PE headers, the SHA-256, other immutable attributes of the software that made and received the connection, the user that executed that software, the container that it was running in, and the device that it was executed on. So software, user, container, and host validated on both sides of the connection to ensure that only legitimate services are communicating. This gets down to a very fundamental level, down to the Python script, down to the Java jar, down to the Ruby script. It's a sub-process validation of software identity using immutable attributes that cannot be manipulated by the attacker without it changing the identity fundamentally. So let's see how easy it is to mitigate these actions. And what we expect to see is, first, we want to stop the systems that are connecting into the command and control system from being able to communicate. Now, we've got multi-platform, Windows and Linux, running in different environments, AWS, on-prem, so on and so forth. So what I want to do is use one policy to completely cut off all of this communication. What we're going to do is log into the Edgewise platform. Edgewise, I need to give a little background on what we're seeing here. Edgewise divides the world into two object types. You've got host segments, which are groups of hosts, and app collections, which are groups of software. So in this particular case, we're going to take the admin tools object. Admin tools is defined very simply as this list of 9 pieces of software running on any device in the environment. So what we're going to do is take the admin tools and look at its connections, map the connections. This is a map of all communications between these admin tools and all other software. So you can see netcat, nmap, SSHD, Nginx, and these are all of the admin tools that communicate. But note, these admin tools are communicating with the globally routable internet, which is something that by default you don't want your administrative tools to be able to do. So we're going to build a policy that stops the administrative tools from communicating with the globally routable internet without disrupting other administrative tools that need that access. So we'll go to Policy Builder and we'll say Administrative Tools, and we'll add the globally routable internet. And we'll say Global Unmanaged from Admin Tools is blocked. Within a couple seconds, what we're going to see here is that all of these communications that are happening from these bootstrappers are going to stop. And there it is. For LinApp Pay 01, LinUserDB 01, AD02, one policy covering both Windows and Linux, those communications are severed. Now, for legitimate communications that need to happen, for instance, the adminscript.py, I can still use adminscript.py to communicate with the internet. This is downloading some data from google.com. So my administrative tools continue to function, but the attacker's tools do not. And to further that point, if I were to launch Python and use the interactive Python and say requests, and then say print requests get, and do http www.google.com and get the text version and run that, what you can see is the Edgewise platform can differentiate an interactive Python shell versus the Python script that I executed previously. This interactive Python shell gets a permission denied, whereas the admin script is able to communicate. So sub-process level software identity verified on both sides of the connection to prevent malicious software from gaining access it should not have. Now, what about preventing installation? If I take one of these systems and I clean it up so that it doesn't have the bootstrapper or preloader, what I'm going to do is say cron-tab-e. I'm going to get rid of the persistence and then psef grep python, and I'm going to kill this. You can see that it's gone, it's cleaned up, and it's not coming back. So now what I'm going to do is go back to my watering hole. I'm going to copy the benign-looking script, and I'm going to paste it in. And the question is, was this effective? You can see our command and control system is running. Now, did it get persistence? Nope, no persistence. Is it running? No, it is not. This protection isn't just about preventing the backdoor from communicating with the command and control system. It actually mitigates the process of installation as well. So this is really multifaceted protection here. Last but not least, are we able to bypass the protection? Perhaps by removing Edgewise. So let's do a look around for Edgewise. We see Edgewise here. What I'm going to do is I'm going to do a sudo kill-9 on that process. So as root kill-9, the most severe signal you can give it, and let's see what it does. No, you can't kill the process. Edgewise actually protects itself to prevent the attacker from killing the process or removing the software entirely. Really what this all boils down to is we've simplified the process of microsegmentation, leveraging identity and automation down to a single click. You can fully microsegment your environment, whether doing administrative tool protection or full-blown microsegmentation with a very simple set of policies that cover all of your environments, all of your platforms.